Okay, so what do we got here? We have two masses. We have a mass of 1.83 kilograms, and then we have a larger mass of 3.03 kilograms, right? So what are the forces acting on this system here? Let's draw them in here. Let's look at both of these objects, and let's draw the forces acting on them. Okay, so I heard gravity. Okay, so I've got a force of gravity acting. This one has weight, doesn't it? Right? So this force has, we're going to call that M1G. M1 is going to be the smaller of the two weights, or masses. Okay? And then over here we've got gravity, and that's going to be a little bigger vector. We'll call that M2G, where M2 is 3.03. Okay? What else? Anything else acting? Okay. Nothing else acting? Ah, there's tension, isn't there? Okay, there is some tension. Now the tension, here's the thing about tension. If those pulleys are massless and frictionless, which they are, right, then is the tension, tell me about what the tension is going to be in that line, like in different places. Is it going to be different there than it is there? It's not. It's not, because they're frictionless and massless, and so think of it this way. If the tension were greater there than there, wouldn't this pulley just adjust itself a little bit to equalize the tension? Yeah. Right? So would everybody agree that the tension in this situation is going to be the same every place? Right? So if I look at each of these two objects here, in this case I've got some tension pulling upward, and in this case I've got some tension pulling upward. Right? Everybody agree? Okay, so if I wanted to write this then as, if I want to write these two free body diagrams separately, look what we get. Let's take this one over here. So this one over here, we know what the mass is, right? And we've got the downward force of M1G and the upward force of T. For this guy over here, we've got the downward force, M2G, and the upward force, T. Okay, so let's write out our equations of motion for these two. Okay, what's the equation of motion going to be for object number one? What's the net force going to be?
T minus M2.
Okay, T minus M1G. Everybody agree? So T2 minus M1G equals what? M1 times A. Okay? Okay? And for now, let's just call that A1. Okay. What about the equation of motion for object 2?
T minus M2G equals M2.
Okay. T minus M2G equals M2A2. But I want to ask you if this, okay, but in this situation, think what we're just saying here. We're saying that if there's some net, well, we have to define some direction that this system is moving, right? Because this is a little more complicated, because this line is attaching these two masses, right? So we need to define, as the system moves, would you agree that this one going up and this one going down are going to happen at the same time? Everybody agree? And so it doesn't really make sense for me to say that the motion of this one is going to be positive and the motion of this one is going to be negative, let's say, right? because they're really, the motion of the system is gonna be in one direction. Think of it like, almost like a wheel. So let's make one little change here. Let's just say that things moving counterclockwise will be positive. Okay? Make sense? Imagine if we were to come up with a similar situation where, let's say that we, instead of having pulleys, let's say that we just stretched out the masses on a frictionless table, and we were gonna pull in the left direction, we're gonna pull with a little force equivalent to the weight of this one, and gonna pull to the right with a force equivalent to this one, right?
There's more intention pulling this way.
There would be a little more pulling this way, wouldn't there? Right? But then, would you agree that the whole system would be moving to the right in the same direction? Everybody see that? So we'd probably call that the positive direction.
Wouldn't there be more tension going that way? Because if you're pulling the bigger weight with the smaller weight, like, wouldn't you have to like use more force to pull?
Okay, but we're saying that these are the forces that are acting, though, right? The tension in between. So if I were to draw that other picture, I want you to see this. If I were to draw, so here's our flat surface, right? Here's the small mass, call that one M1. Here's the big mass, M2. The tension is what is acting in the line between the two, right? And now, instead of gravity acting, let's just say that we had some people pulling on this end with a force equal to the weight of this one, and we had someone pulling on this end with the bigger force equal to the weight of that one. Does everybody agree that the system is probably going to slide to the right? Because this force is bigger than that force is, right? Everybody see that? Okay, so then that means if the motion is in this direction, we would say, for example, that this must have been a negative force acting backwards, and this must have been a positive force, let's say, right? Everybody agree? And the tension would actually be pulling M1 in the positive direction, but it would be resisting the motion of M2. So it would be pulling it in a negative direction. Agreed? Okay? So using this diagram right here, it's pretty easy to see that if we do this, right, we've got, remember that was just equal to M1G. This was equal to T. This guy over here, we had T pulling in that direction, and that was just pulling with the weight of this thing. That was the force we were using. So now the free body diagrams tell us that the equations of motion are a little different than what we got there, didn't they? Because look, this one here we said, okay, T is in the positive direction, and M1G was in the negative direction, but this is then backwards, isn't it? Right? Because in this picture right here, we can see that the positive force is M2G, and the tension is actually pulling this bigger object in the negative direction, right? You see the dilemma? So when we look at this page, we've got to define this convention that as the system moves clockwise, we'll call that positive. So we got to change this equation. How? Because this is the positive direction, right? Clockwise. And so which one of these two forces should be positive?
T.
No.
M2.
M2G, right? Because this is starting here and moving around like that, we're saying is positive.
M2G minus T.
Right. M2G minus T. Okay? Okay, but what about the acceleration of the two masses then? Do I need to call those A1 and A2? How come? They're the same, because they're tied together, right? Does that make sense? So that helps. One thing I could do is I could eliminate those subscripts, because they're all part of the same linked system. It's just one acceleration for the whole system, right? Now what were we trying to do with this? I lost track. We're supposed to find the acceleration of the smaller mass, which is the same as the acceleration of the bigger mass. We're just trying to solve for A, aren't we? Okay. I've got these two systems here. Well, what could I do with these two systems? I mean, the system of two equations. How am I gonna solve this thing? How many unknowns are in this?
2. Well,
I see, yeah, 2, because we know M1 and M2, those are given to us, right? But we don't know the tension and we don't know A. So what do I do with a 2x2 system, if you think
You could,
mathematically?
divide the bottom one by M2 and then set A, insert all those stuff that's on the left into A.
Okay, so what River's suggesting here, let me translate that. He's saying solve for T in one of these equations and substitute, right?
but A's in both equations, so I don't.
That's okay,
No,
that's
yeah,
okay.
that's the point.
Because if T, the variables T and A are in both equations, then that means that I should be able to solve for one in terms of the other and substitute to get rid of it, right? Does everybody see that? So if I were to, for example, solve for T in the top equation where it's a little easier to do, right? T would just equal M1A plus M1G, right? I could take that expression and plug it in there, and the T's would be gone, and I just have more, I'd have another A in there, but that's all right. I can, if there's a single variable, I could add up like terms and solve. Everybody see that? Okay, there's another approach to this. This is kind of interesting too. There's a principle in physics and math, we use this a lot in physics, called the principle of linear superposition. Big fancy word, but it just means when you study linear algebra, you'll do more of this, that if I have two linear equations, I can add them together to get another linear equation, which is consistent with that system, right? This is a great shortcut. So what would happen if I were to add these two equations up?
Is it M1 equals M2?
Yeah, well, look what's going to happen there. If I add these things up,
Lost.
I get T minus M1G plus M2G minus T. I'm going to get positive T plus negative T. Those cancel. Everybody agree? Okay. And so look what happens on the left side then. I get M2G minus M1G equals, and on this side, I'm just going to get M1A plus M2A, right? Okay. Now, I could then, we're going to look back on this in hindsight and say, well, maybe we could have tweaked this just a little bit and made this a little simpler. So I could factor a G out of that, right? Because M2 times G minus M1 times G, isn't that the same thing as the quantity M2 minus M1 times G, right? And on this side, M1A plus M2A, isn't that the same thing as M1 plus M2 times A, right? We're trying to solve for A, aren't we? Okay. So we could divide each side through by that factor. Agreed? So those cancel. And look at my result then. I get the result, A equals the difference of the masses divided by the sum of the masses times G, right? Okay, everybody see that? That makes sense. Let's look back at our picture, and that makes perfect sense. Okay, did we really need the tension there? Did anybody get this one right? Get this problem right? Okay, if you did, I was kind of hoping maybe, this is a tough one, but there is a way we could make this simpler. Does the tension really do anything? If we're considering the system of the small and big mass, does that tension really, it acts inside the system. In fact, we call that an internal force, right? So if it really doesn't make any difference, does it? So if we're going to look at this system of the two masses together, well, the tension is just linking them together, right? What are the forces acting on this system? Well, we've got one force acting in the negative direction, that's the weight of the small, right? Because we said the positive direction was twisting or rotating to the right, clockwise. So we've got a negative force that's the weight of the small mass and a positive force that's the mass of the big mass, right? The weight of the big mass. And so if I wanted to turn this into maybe a simplified free body diagram, I could have just done something like this. I could have said there's one force acting in the positive direction, that's M2G, and there's one force acting in the negative direction, that's M1G, and what's the mass of the whole system? Because it's all being accelerated, isn't it? Because they're linked together, right? The mass here is really M1 plus M2. That makes it way easier, doesn't it? Right? You see what I'm saying? And so this was pretty simple then. What's the net force? If we turn this into, let me just grab this.
Wow.
That's pretty cool.
Isn't that cool?
Oh.
There we go. Okay. So if I turn this into an equation of motion, well, isn't that just net force is going to be M2G minus M1G, positive, negative, right?
Oh my.
Equals the total mass, which is M1 plus M2, right, times A. And so A is just what we got. Isn't that pretty cool? Right?
So we know what G is, right?
Yeah, so if we divide both sides by this, so we could rewrite this, I could factor out the G like we did before. M2 minus M1 times G, just like we did before. And then divide each side through by M1 plus M2. Right? And that's the same answer we got before, right? Just a lot quicker. We just kind of removed the middleman, right? Because once again, those tensions, they didn't really do anything. They were just, it's all internal. But what's really cool about this is the two were completely consistent, right? We could do this involving each of those two masses separately and sharing a tension, or we could think of them as being bound together and being one mass, one big mass of M1 plus M2, right? See what I'm saying? Okay? Yeah, I think that's very cool. It has to be that way too, doesn't it? Right? If you think about, and I wish I had this set up to demonstrate, I really like this problem. What if I had a 2 kilogram mass hanging and a 1 kilogram mass hanging, right? Then the net force is going to be, I'm going to have roughly 20 newtons pushing down this way and roughly 10 newtons pushing down this way. So what's the net force going to be? 10 newtons acting this way, right? So the whole system's going to move this way because that has a larger mass hanging, right? But it's not going to accelerate at 9.8 meter or roughly 10. How come? Well, because that net force has to pull both masses, not just, see what I'm saying? It's got to pull both of them, right? And so what if they were very, very evenly weighted? What if I had 1,000 kilograms or 1,001 here and 1,000 here? There's only one extra kilogram, so there's only 10 newtons hanging extra on this side to accelerate 2,001 kilograms. That thing's just, it's just going to creep. It's just going to barely even accelerate because there's barely any net force compared to the total mass of the system, right? That principle of exaggeration is helpful. If you think about really large quantities, sometimes it makes it easier to see, this relationship, to sort of visualize it. Okay? That makes sense? I recorded it, so if you got to watch it again, there it is. All right.